Families sleep shoulder to shoulder on raised platforms, while smoke drifts toward the ceiling. Outside, the temperature plunges below freezing. Inside, children sleep warm. This is a Haudenosaunee longhouse.
A structure that stretches over 200 feet and houses more than 20 families under a single curved roof.
For 6 months each year, from mid-October through mid-May, these communities remained sealed inside. Against brutal cold, deep snow, and relentless wind, survival depended entirely on architecture. The question isn't whether they built a shelter. The question is how they engineered a wooden structure. Using only saplings, bark, and rope to generate enough warmth for dozens of people, store 6 months of food and firewood, manage toxic smoke from multiple fires, and maintain breathable air, all without metal fasteners, mortar, or modern insulation. The Haudenosaunee referred to themselves as the people of the Longhouse. The name wasn't metaphorical. The building defined everything: their social structure, their political confederation, their survival through winter.
To understand how they lived, you must first know how they built. The Longhouse began with a problem of materials.
The woods remember when we were young.
The virgin forests of the northeastern woodlands grew massive trunks, oaks, and too wide for stone axes to fell efficiently, too heavy for work crews to haul and position. Attempting to construct with these giants would have consumed months of labor for a single structure. The Haudenosaunee solved this by targeting second-growth forests. These were clearings where older trees had died or been removed, allowing younger growth to surge upward in competition for sunlight. The result was dense stands of straight, slender saplings. Cedar, hickory, and elm, sized for human handling. Trees between 4 and 8 inches in diameter.
Could be felled, stripped, and shaped in hours rather than weeks. Material selection extended beyond convenience.
The framework required 2 types of wood with opposing properties. Vertical posts needed stiffness to bear the roof load. Rafters needed flexibility to bend into the characteristic barrel vault without snapping. Young saplings provided both. Thicker specimens became posts. Thinner, greener saplings bent into arches. Construction timing wasn't arbitrary. Building happened in late spring and early summer, when sap flowed heavily through the cambium layer beneath the bark. This narrow seasonal window served 2 purposes. First, the moisture made young saplings pliable enough to bend into smooth curves, without fracturing the wood fibers. Second, and more critically, the sap flow allowed builders to harvest bark in massive sheets, without prematurely killing the donor tree. Elm bark was preferred. A mature elm could yield panels, measuring 3 feet high and 6 feet long, large enough to cover substantial sections of framework with minimal seams.
The harvesting technique required precision. Builders made vertical cuts down the trunk.
Then horizontal cuts at the top and bottom. During peak sap flow, the bark layer separated cleanly from the sapwood beneath, peeling away in flexible sheets that could be rolled for transport. The framework rose in stages. Vertical posts were planted in pairs along 2 parallel lines, spaced 20 feet apart. This width became standard, narrow enough to span with available rafters, wide enough to accommodate a 10-foot central aisle with 5-foot living platforms. Along each wall, post pairs were positioned every 20 feet down the length, creating modular compartments that could extend the structure to 30, 60, 100, or even 200 feet, depending on the size of the extended family group. Crossbeams connected the post tops, forming a rectangular frame. Then came the critical innovation. Young, flexible saplings were bent from one side to the other, creating the rounded roof profile. This barrel vault shape wasn't decorative. It was thermal engineering. The entire frame was held together by lashing, long strips of bark.
Typically basswood or hickory, braided into rope. No nails, no wooden pegs, no notched joints.
Every connection consisted of carefully wrapped and knotted bark cordage. This choice seems primitive until you consider the environmental forces. Winter brought extreme temperature swings. Wood contracts in cold, expands in warmth. Frozen ground heaves upward with ice lenses, then settles in the spring thaw. Wind loads shift constantly. Rigid connections, pegs driven into drilled holes. Notched timbers locked at right angles crack under this repeated stress. They fail catastrophically. Lash joints flex. When wind pushes against the structure, the bark rope absorbs the force through slight movement. When frost heaves the ground, the frame adjusts rather than shatters. The entire building breathes with environmental stress. This dynamic stability, not static strength, kept longhouses standing through decades of seasonal extremes. Two lashing techniques dominated. Square lashing secured perpendicular joints, vertical posts to horizontal crossbeams. Diagonal lashing joined poles meeting at different angles, particularly the cross braces that prevented the frame from racking sideways.
Each technique required knowledge of tension, friction, and binding geometry, which was passed from builder to builder.
With the skeleton complete, cladding began. Bark panels were lashed to the outside of the framework in horizontal courses, overlapping like shingles. Orientation mattered. Tree bark grows with vertical furrows. Natural channels that would funnel rainwater directly down the wall if positioned vertically. By lashing the bark horizontally, these furrows ran parallel to the ground. Water hit the outer surface and sheeted sideways off the building, rather than penetrating seams. Some builders went further, using a stone adze, a cutting tool with the blade perpendicular to the handle. They smoothed the horizontal furrows on each bark panel before installation, creating an even flatter surface that shed water more efficiently. The final weatherproofing step involved a second layer of poles lashed to the exterior, directly over the bark cladding. This outer lattice pressed the bark sheets flat against the inner framework, preventing wind from catching edges and peeling the weather barrier away. The result was a triple-layer shell, an inner frame, bark insulation, and an outer compression lattice. With the walls sealed, the structure faced its central paradox. Fire generates heat. Heat sustains life. Fire also produces smoke. Smoke kills. A longhouse 200 feet long housed 20 to 30 families, 60 to 100 people. Cooking, warmth, and light all depended on open flames. A single central fire couldn't heat the entire length. The solution was distributed hearths, one fire pit in the center aisle of each 20-foot compartment. A 200-foot longhouse might contain 10 separate fires. Burning simultaneously, 10 fires produce massive volumes of smoke. Without ventilation, the interior would become uninhabitable.